Okay. Hello. Wait. Okay. Hello all. Welcome to feedback video for module 2. My name is Nia. I'm the moderator for this MOOC, and here I have Elizabeth and Pablo, who will be discussing what we saw for this week.
Yes, hi everyone. First of all, we would like to start by thanking everyone for such an active participation in the discussion forum. It has been great to see all of your comments, all of the questions, and we will be processing all the feedback on the coming days, so you can expect a lot more activity there. In the meantime, we were really happy to address some of the points that have been brought up and to highlight some of the assignments that have gone really the extra mile. So first, we would like to address some of the open questions and the responses that we got to our question on how can we prolong the lifespan of the timber elements. Some of the considerations that were mentioned have to do with aspects that are taken into account the early stage of the design of a building. So some users focused on recommendations that have to do with the design in a modular way, with how to build with dry connection systems. And these decisions can, of course, facilitate the adaptation of the building to satisfy future demands and also to facilitate renovation. So in this case, I was wondering, Pablo, if you would like to introduce maybe an example of this?
Yes, for sure. I also really liked the discussion. And it made me think of this project, which just won the National Timber Building Prize in the Netherlands. It's an energy company, Liander, in Amsterdam. And if you look at the design of this building, it is right in the harbor of Amsterdam. You see it here. And it's designed as an office building. But the architect took into account making an open grid that it's also potentially adaptable to become residential building in the future. So it also touches upon the aspect of flexibility. And then next to that, it's also really built in a demountable way. So this is the sketch that the designer thought of in the beginning, right? And you also see that the climate installations are separated from the main timber construction. And if you look at the building site, you see all these large elements, and you see here that very smart, well, in this case, steel connections were designed, but for dismountability. So these long beams click more or less in these seams. They are then bolted or screwed to attach them. And then when you look at the final building, what the architect had in mind was this. And this is what it looks like in the end. So it's a real marvelous building. And you see that the bearing structure is also directly the finishing. So it also decreases costs for that matter. And it makes it totally demountable. And here also you see the climate installations, which are just screwed on onto the CLT. So really dry connections and designing for dismountability. So I would just love to share this really recent example.
Yeah, that's actually quite a beautiful example. And to add up a bit on that, a few users also mentioned a very important aspect, which has to do a lot with how it's necessary to change our perspective to fit long-term sustainability strategies. And this has to do with, instead of thinking on only demountability, thinking on actually adaptability. Because designing for demountability is really just a part of the solution, and it should actually be one of the last resorts, in the sense that it's better to first design for the buildings to be durable, to be flexible, and try to maintain the integrity of the load-bearing structure as much as possible, so that it can be later on adapted to future functions, but maintaining the integrity of the elements. Something that we mentioned, of course, as well in the forum was that we don't know what the world is going to look like in 50 years exactly. So this design for this assembly is, of course, to enable the timber to be kept at a high value so that it can be then later on reused and later on then cascaded. So,
and maybe Elizabeth to add, because timber is 5 times lighter than, for example, concrete, and usually concrete is cast. So timber is a very good material for dry connection. So this is also offers a lot of opportunities.
Exactly, yeah. And to follow up a bit on that one, there were a few users that mentioned the concern with the chemical glues that are used on engineered timber. So I was wondering if you could just recap real quickly what your expert opinion is on this regard, Pablo.
Yes, so it's good to know when you look, for example, at CLT, it is connected with a low percentage of glue, 1%, and with other products such as laminated veneer lumber, it can be up to 4%. But these glues, these are synthetic, that is true. So there can be an improvement to make them fully bio-based. And some glue companies are working on this. For now, what I've seen in the market, those alternative glues are a lot more expensive and don't have the same performance yet. But I'm sure in about, well, 5 to 10 years, we'll see some major breakthroughs there. In the meantime, I don't see it as the biggest problem, because such a piece, for example, a CLT, if we design it in a demountable way, in the end of life, we will just reuse it. This timber, as long as it stays dry, will last forever. Look at our medieval kennel houses, for example. You actually just would need to shave it or sand it, and you can reuse it. And maybe in a second life or third life, you can chip it to produce particle boards. They add a little bit more of the glue in the resin. But and only in a fourth or fifth life, you should maybe burn it for energy production. What is good to know, there are a lot of course, mandatory emission tests, indoor emission tests that any indoor material has to go through to come on the market. For example, in Europe, there are very strong threshold values. And they've done testing on all these timber products, and it's around 10% of the threshold value in terms of VOCs, volatile organic compounds. So the indoor emissions of these glues are really very low. And then if you would burn them, they could be burned, they would be considered as B wood. So C wood is with very toxic chemicals, for example, when you preserve it for with biocides. That is what you don't want. But this kind of glues are considered B wood. So that really facilitates reuse or recycling for particle board, OSB, or other board materials. And in the worst case scenario, you burn it for energy production. It's in a biomass energy plant, and the emissions are really not that severe compared, for example, to plastics or other materials or wastes that we commonly burn in our waste incineration plants. So yes, it's the last resort, but I don't really see it as the biggest problem. Yeah. There are solutions, for example, where the glue is substituted by dowels. That's called dowel laminated timber. But in that case, you need really a lot of more timber to meet the same span. So for me, it's really not the biggest problem, but I think it will be good in the future to have 100% bio-based glue for sure.
Yeah, and that might be just a matter of time, hopefully. To follow up a bit on one of the last points that you were mentioning, Pablo, regarding the end-of-life scenarios, some users were as well very surprised that incineration with energy recovery is the default scenario for the treatment of timber elements. And in my experience working a lot with environmental product declarations of companies, I've started to notice that newer EPDs are actually coming with the scenarios of reuse and recycle as alternative to the incineration with energy recovery default. So we are hoping that in practice, of course, what we recommend is to first prioritize the high value reuse of the structural timber, followed by cascading and opting for incineration with energy recovery as really the last resource. And landfill, of course, should generally be avoided. And I wanted to also mention that with timber, you have, of course, a considerable amount of carbon that is stored in these elements. And some of the results of the exercise of first week was, of course, people showing all these timber structures, a lot of them that have existed for more than 100 years. So this really shows the carbon storage potential that we can have in the building stock by building with structural timber. I would think indeed then the priority should be to delay as much as possible the incineration of timber so that we can prioritize climate change mitigation strategies. And of course, opt first for the reuse and the cascade. To facilitate the reuse and the cascade of the timber elements, some people mentioned, for example, that it's important to have building material passports and also maybe use QR codes for identification, which is, from my understanding, a common practice already in the industry, right?
Exactly. So that is right now the practice, and you see some of those suppliers that even have a take-back guarantee. So they see big mass timber elements as a kind of well, also material database, a material bank that contains and retains its value. And by making sure that the timber will come back, they will close the loop. And well, in the end, it's just also economic business case they will look at. And personally, I don't think it will be allowed in 50 years or something to burn wood and emit the CO2 that's attached to it.
Yeah, hopefully. I should make just a quick note. It's still also unbelievable for me that a lot of the decarbonization pathways consider or are heavily reliant on using biomass for energy production. So this is something that I think governments are going to need to work through to make sure that biomass elements such as structural timber are not used priority to, let's say, substitute natural gas or other fuels in order to aim for a decarbonization pathway, but to actually exploit the potential of structural timber on the building stock as a carbon storage potential. But now, just to wrap it up as well, I would like to switch now to give a bit of feedback on the assignments that we saw for week 2, for which we had provided an exercise in Ubacus. I have to say we were very pleasantly surprised to see the variety of strategies that we saw by everyone modifying their wall structures, and also all the interest that the users expressed in the outcomes of this assignment, and also, well, Ubacus being one of the many other tools that can be used to both assess the structure of building performance, but also from an LCA point of view. And just before we dive into a few examples, I wanted to clarify that Ubacus shows the climate change impact from a cradle-to-gate boundary system. So for those that might not remember, on the video we explained that cradle-to-gate refers to the modules A1 to A3, which have to do with the manufacturing of the material themselves. And in this case, the negative climate change impact that we are observing while modifying the structure has to do with the fact that the carbon stored in the wood, oh, sorry, I'm gonna lift to turn on the light again. We have smart energy measures installed. I just wanted to clarify indeed that the carbon that is stored in the wood is counted as a negative credit on the module A1 to A3. And the carbon that is stored in these materials is sometimes bigger than the positive emissions that are emitted throughout module A1, A3. So this is just to clarify a bit why the climate impact potential shows up as negative when enough amount of biomaterials are considered. So I was wondering if you would like to highlight a few examples, Pablo, that you found interesting from this exercise.
Yes, for sure. Maybe you can show 2 up. Actually, we were really impressed by the many high-value entries. So it really worked out very well, this assignment.
Yes.
Yeah, so maybe you can share your screen.
The first one, I don't know if you can see it now, if I should zoom it.
Yeah, maybe a little bit. This is just random because there were so many very good examples. So this is one of them. And what we really liked is that, well, our main purpose was to show that in the build-up of a construction, and you can just choose alternative bio-based materials. When they come from sustainably managed forests, we know that they are carbon negative because of the biogenic carbon. So if you switch bricks to, for example, most timber species, then you'll see that in the end it turns to a negative number. What is interesting is that with a couple of assignments, you went the extra mile and really made a build-up of the details, and including, for example, from inside to outside, should there be a vapor barrier or a moisture barrier? And of course, you need this. And of course, it could add a little. This is also a material choice that can maybe add up to the carbon footprint. And also, so there are many other considerations when building up your wall or floor system. In this case, our only purpose was to show that if you replace, for example, synthetic insulation like rock wool with bio-based insulation, it can be cork or it can be cellulose or many others, the emissions will go down, become carbon negative because of the biogenic carbon storage and the lower CO2 emissions. But also, if you play around with it, the heat transfer or the U level, the U value will also can be the same, just depending on the kind of material you choose. But there sometimes is a trade-off, right? Sometimes you need a little bit more insulation when it's bio-based compared to a synthetic material. So for this specific example, someone specifically looked at outside. I want to see a timber building, which also looks like a timber building. This is not necessarily needed, but it does help in terms of carbon footprint. And here, this learner chose, after an analysis, which is really good, chose Western Red Cedar, which is quite a good cladding material. And I just wanted to point out, because there were also a couple of questions about that on the forum, that there are a couple of modification technologies, which is called wood modification, which changes wood or bamboo or any other bio-based material on molecular level. So instead of impregnating with biocides, this is just a heat treatment. For example, thermal wood, here's an example of thermally modified bamboo. This increases the resistance, makes it very stable, up to a durability class 1. That means it's the highest durability class, and it will hardly or it will not rot even in ground and water contact. Another example is acetylated woods, which goes through a vinegar treatment. This is a piece. Well, you can smell it. I can smell a little bit of vinegar in here, but this makes the timber totally rot resistant, gives a guarantee of 50 years outside. So it shows that there are very good examples also on the outside of a building for the cladding. That can be timber. It doesn't have to be timber, but there are very weather resistant examples. In this specific example, the learner chose I-Seam. So that's a kind of new insulation material with very good heat value, similar to the rock wool, but at a very low carbon footprint. And well, that is what this is about. There are many things that you can take into account: cost, thickness of the wall. But if you just look at the environmental impact, it really makes a difference if you choose all the materials in the right way. So, well, that's what I wanted to say on this on this specific example. Elizabeth, you have anything to add, or we go to the next one?
Yes, I just wanted to mention indeed that it was also very interesting. Some people mentioned that sometimes there are additional considerations to take into account, such as budget or even material availability. So it was great to see that some of them also really took the time to explore all the other bio-based alternatives for insulation materials and cladding indeed. To see that actually aiming for carbon neutrality can be a combination of different strategies and not a single one. So that was great to see as well. We cannot mention all of them because indeed there were a lot of really cool exercises, but I was happy to see that as well. And well, I think it's good to now wrap it up. I would like to thank you everyone again for the involvement in the course, and I'm looking forward to staying in touch on the discussion forum as well in the coming weeks. And yeah, I think that was mainly from our side today.
Yes, we are very excited about all the good input. And do take a look at the forum, because there are many good examples where you can learn from yourself. One final point I wanted to mention, Elizabeth, there was also a couple of students that looked, for example, even when that thorough and look at the condensation point, right? Where if there's moisture in your construction, and if it gets too cold, there can be condensation. So really some very interesting examples that even we learned from.
Yeah, I agree. Indeed, it was the vapor layer as well, right?
Exactly.
Yeah, that was great to see. Yeah.
Thanks for that. And also some students mentioned the layers of brand, which is also something to maybe really recommend to take a look on. Because if you design for dismountability, then you have a superstructure, which might last 100 years. But for example, the skin will last 20 to 30 years. So if these layers are designed for dismountability in their separate layer, this will also really help the dismountability and the circularity potential.
Exactly. I think there was one specific exercise where they had designed an extra layer so that if there's any changes in installations needed, that does not disrupt the CLT. So
Exactly.
yeah, I encourage everyone to check out the files that have been submitted on the Sketch Drive. If you have any questions, feel free to post it on the discussion forum, and we're gonna try to keep up with all the feedback and comments.
Well, thank you, Paolo. Thank you, Elizabeth, for giving such an amazing overview of this week's assignments and posts. And thanks for everyone for their activity and engagement just overall in the course.
Thank you.
All right, thanks. Ciao.